Curvilinear coordinate systems 19. Consider a sphere of radius r0 rotating at a constant angular rate omega 0 about its z-axis so that omega is equal to omega 0 ez hat. And now we're going to perform the surface integral, closed surface d sigma cross with v over the entire surface of the sphere. We have calculated what v is in part A. So this is our velocity vector v. Therefore, we need to find our differential area d sigma. So what we're after is the closed surface integral d sigma cross product with velocity v. And d sigma is a vector that points radially outward from the sphere. So it's a surface area h theta d theta h phi d phi, and it's radially outward, so it's in er hat direction. And we have calculated the scale factors h theta and h phi, so we obtain r square. One of them was r, the other one was r sine theta, so we obtain r square sine theta, the polar angle theta, d theta d phi in er hat direction. So let's check our scale factors here. We found h phi to be r sine theta and h theta to be r, so the product is r square sine theta. Well, in this case, r is equal to r0, so it's going to be r0 square sine theta d phi in er hat direction. Now our task is to calculate d sigma cross product with the velocity vector v. So here is our d sigma vector, and we're going to take a cross product with our velocity vector. So let's copy our velocity vector here. And here is our velocity vector. Now we encounter the cross product er hat cross with e phi hat. And here is our cyclic permutations for this coordinate system. So if I copy that here, I can figure out what this would be. And we're looking at er hat not cross with e theta hat, which is the positive direction, but er hat cross with e phi hat, which is in the negative direction. So that is going to be in the counterclockwise direction, which is negative. So that will give me minus e theta hat, you can see here. So for this cross product, I have omega 0 r0 cube. So I have omega 0 r0 cube. And I have one sine theta here, another sine theta here. So this is going to be sine square theta d theta d phi, the azimuthal angle, and the cross product er hat cross with e phi hat I find to be minus e theta hat from the cyclic permutations. Er hat cross e theta hat is e phi hat, er hat cross e phi hat is minus e theta hat. So if I substitute that to my integral that I'm after, the closed surface integral, d sigma cross v, this will be equal to omega 0, which is a constant, r0 cube, that's a constant. The integrals, two integrals, one integral is over theta, the other one is over phi, and this is done for the whole surface of the sphere. So as for the theta integral, I will have 0 to pi. For the phi integral, I will have 0 to 2 pi. So 0 to pi basically covers a full hemispherical region where I have a slice, and that slice is then rotated by an angle 2 pi about the central axis so that I cover the full sphere. So this is going to be now sine square theta d theta, and this integral is what I have to calculate for the theta part. And here I have a d phi integral, and the whole thing will be in minus e theta hat direction. Okay, so this will be omega 0 r0 cube integral from 0 to 2 pi d phi and then for the e theta hat part, I have a position dependent unit vector here. So this will give me integral 0 to pi sine square theta d theta, and then I have to substitute minus e theta hat. So let's put the minus sign here, and for e theta hat I have to look at what I have found. E theta hat is here, so let's copy that. This is our integral, and here is e theta hat. All right, and now we can perform this integral, the phi part. I'm going to have minus omega 0 r0 cube integral from 0 to pi, that's for the theta integral. Now if I perform the phi integral first, you can see that here I have sine square theta, cosine phi. The cosine, I can also take the sine square theta out because that doesn't contribute to the phi integral. Sine square theta d theta. I have what is left here, a cosine theta and cosine phi. An integral of cosine phi is sine phi, so this will give me sine phi cosine theta in ex hat direction. And then I have, for the next term, a cosine theta sine phi. The sine phi integral will give me a minus cosine phi. So this is going to be minus cosine phi cosine theta in EY hat direction. And then here I have sine theta EZ hat, which doesn't have any phi in it. So the integral will give me just minus phi. And this integral has to be evaluated between phi is equal to 0 and phi is equal to 2 pi. All right. So let's take a look at what I would get here. If I substitute phi is equal to 2 pi or phi is equal to 0, this term would give me 0. If I substitute phi is equal to 2 pi here, for phi is equal to 2 pi and phi is equal to 0, cosine phi is the same thing. So that would also give me 0. So only this part would give me minus 2 pi minus 0, which would give me a minus 2 pi. Multiplied with this minus, it would give me a 2 pi. So here I have 2 pi from the phi integral, omega 0 r0 cube, integral from 0 to pi, here I have forgotten a sine theta EZ hat minus phi sine theta EZ hat. This is to be evaluated between pi equals 0 and 2 pi. Therefore, I will actually obtain here also sine theta EZ hat. So this would give me sine cube theta with the sine square up front, sine cube theta d theta in EZ hat direction. All right, and we can now perform the theta integral. 2 pi omega 0 r0 cube, integral from 0 to pi, theta equals 0 to pi, and sine cube theta can be written as sine theta and sine square theta, which is 1 minus cosine square theta d theta in EZ hat direction. And this will give me 2 pi omega 0 r0 cube. The integral of sine theta will give me minus cosine theta. That will be evaluated between 0 and pi. And then I have minus the integral from 0 to pi sine theta cosine square theta d theta, and this will be in EZ hat direction. Now we obtain 2 pi omega 0 r0 cube minus cosine theta and in order to perform the second integral, I do the following substitution. U is equal to cosine theta and du is equal to minus sine theta d theta. Therefore, you see that I have here u square du. Integral of u squared du is u cube over 3. So this is going to give me plus cosine cube theta over 3 which will be evaluated between 0 and pi in EZ hat direction. Now, if I substitute the two endpoints, 2 pi omega 0 r0 cube, cosine pi is -1 minus -1 becomes +1, cosine 0 is +1, and I'm going to get minus. So let's first substitute to pi here. I will get +1, and cosine cube theta over 3 will give me -1 over 3. Then if I substitute cosine 0, which is -1, +1, and there's a minus sign here, so it's -1, and I'm subtracting it from the previous one, so it's going to be +1. And if I substitute 0 here, it's 1 over 3, so that's -1 over 3 because I'm subtracting it. EZ hat. So this is evaluated at pi 1 -1 over 3 minus evaluated at 0, which is -1 plus 1 over 3 subtracted from this. It gives me this result. So this will end up being 2 pi omega 0 r0 cube 2 minus 2 over 3 in EZ hat direction. So I can write my final answer for d sigma cross with v closed surface integral. This is 6 minus 2. I'm going to get 4 divided by 3, but it's multiplied by 2, so it's 8 divided by 3. So I will have 8 pi omega 0 r0 cube divided by 3 in EZ hat direction as the final answer for this closed surface integral. All right, so we worked on this closed surface integral d sigma cross v. First thing is to determine what the sigma vector is. It's this differential surface area vector, h theta d theta h phi d phi in er hat direction. For a sphere, it has to be radially outward in er hat direction. And substituting the scale factors, we find r0 squared sine theta, d theta d phi er hat. And we have calculated the velocity vector v in part A, so we substitute that here. And when we take the cross product, er hat cross with e phi hat, that gives us minus e theta hat. This is in the counterclockwise direction, which is negative. So minus e theta hat is actually a position-dependent unit vector, which is minus cosine theta cosine phi ex hat plus cosine theta sine phi ey hat minus sine theta ez hat. In order to cover the full surface, I have to have theta varying between 0 and pi and phi varying between 0 and 2 pi. If I perform the phi integral first, for cosine theta cosine phi, the integral is sine phi cosine theta. For cosine theta sine phi, it's minus cosine phi cosine theta. For minus sine theta ez hat, it's minus phi sine theta ez hat. Evaluated between pi cos 0 and 2 pi, which only has a non-zero term for the last part, the ez hat part, that gives us a factor of minus 2 pi. So that's here. So we obtain 2 pi omega 0 r0 cube integral 0 to pi sine cube theta d theta in ez hat direction. It's important to note that you have a position-dependent unit vector here. That's the key point in this problem. Integral of sine cube theta is pretty standard. We can substitute for sine squared theta 1 minus cosine squared theta, and then do this u is equal to cosine theta substitution transformation, and we can easily find the answer for this integral, and this allows us to write our final answer, 8 pi omega 0 r0 cube over 3 ez hat.